In the last video we have seen how to solve wave equation in the full domain minus infinity infinity and x is in minus infinity infinity. That is a D'Alembert's solution, and when the wave equation is given in the semi infinite domain, that is 0 to infinity, and you have to provide a boundary condition at 0. So, that you can give in many ways, either you can fix that string. So, it is a model for string when you give initially its displacement and its slope, and you have to provide the boundary at one end of the string, other end is infinite string. So, you do not have to give any condition, but at one end either you can fix it or you can allow it to be free. Free means its slope is 0, that is ux is 0. If it is fixed means the displacement is 0, so that is u is 0. So, u equal to 0 also we solved the equation, we solved the boundary value problem, initial boundary value problem for the wave equation in the semi infinite domain 0 to infinity, when the boundary condition is u at 0 t equal to 0. That means you fix the one end of the string, so the displacement is 0. So, how did we do that? So, we have actually extended all the functions involved as odd functions to minus infinity infinity, and then we made use of D'Alembert solution finally, so that we can automatically. So, the advantage of this is that boundary condition is automatically satisfied, and then we found exactly what is the solution. Okay. So, we have seen that this is the solution, u of x t is this. So, u of x t is this. So, this is your solution, x is between 0 to c t, and you have this solution, and when x is greater than c t, this is your solution. And see, you extended the functions f x and g x as odd functions, that means f of minus x minus f of minus x. When you put x equal to 0, so f of 0 is minus f of minus 0 is 0. So, implies this f of 0 has to be 0, this is 2 into f of 0 is 0, that implies f of 0 has to be 0. So, this has to be satisfied. This is also, this you can see, if you want this to be a solution at x equal to c t, this solution has to be continuous and it is also differentiable, okay, because it is satisfying wave equation which is the second order in both the variables x and t. It is twice differentiable function, and f has to be twice differentiable, x has to be f has to be twice differentiable function, g has to be continuously differentiable. One time differentiability is enough, because u double dash is actually you will get g dash. So, this is only g needs to be only one time differentiable, and f has to be twice differentiable function. So, when you equate u is continuity u at x equal to c t here from the left side, and u at x equal to c t from the right side. When you equate, you will see that f of 0 equal to 0. Okay. So, you can easily see that half, when you put f equal to x equal to c t, f of 2 c t minus f of x equal to c t, that is 0, plus 1 by 2 c 0 to 2 c t g of s t s. This has to be same, right. This has to be equal to that part when x equal to, when you put x equal to c t from the right hand side. So, if you do that, half times f of 2 c t, now this is plus f of 0 plus this is same 1 by c t to 0 to 2 c t g of s t s. So, this gets cancelled and this also gets cancelled. So, what you are left with is f of 0 is 0. Similarly, you can show that g of 0 is also 0. Okay. So, how do you do that? G of 0 means you have to differentiate. Not only that, what you did is u at x t, rather you should say u at the limit x goes to c t from the left hand side minus u x t. This is equal to limit u x t as x goes to c t from the positive side. So, this will give me this gives me f of 0 is 0. Now, if you equate limit u dash, that is you can take u x or u t, anything, okay, anything will work, u t or u x, okay, u t as x goes to c t minus this is equal to limit u t, this has to be continuous, c t minus, because it is twice differentiable. If you want to say that u is the solution, it has to be continuous and its derivatives have to be continuous. So, this will give me, actually you will see, you can, if you do the calculations, you will see that g of 0 is also 0, because g is also, you extend it as odd function. When you put x equal to 0, you see that g of 0 is also 0, okay. So, that is how you can easily, these are automatically satisfied if you want this to be solution. This is a solution because you extended as an odd function, that implies automatically g of 0 is f of 0 or 0, that is clearly you are satisfied because u is the solution, that is how you found the solution, okay. The same way, now if your solution is, so we have seen from 0 to infinity, when this is when the string is given, you attach now at the boundary you allow it to be free, that means u x at 0 t is equal to 0, that means dou u by dou x at 0 t is 0. So, if you give this condition, this is your t, this is your x. So, you have here u t t minus c square u x x is 0 inside this domain, and you have two initial conditions here at t equal to 0, and here you provide this boundary condition, this one. So, that if you write, so the boundary value problem, initial boundary value problem, like u t t minus c square u x x equal to 0, x is only positive, semi infinite string, t is positive, and you have u at x 0, initial condition is f x, u t at x 0, that is g x. These are your initial conditions, and boundary data is u x at 0 t equal to 0 for every t, and here for every x positive, that is what is given. So, such a boundary value problem, we can solve again by making use of the by making use of the D'Alembert's solution. If you want to use a D'Alembert solution, you have to extend this to the full real line. So, because of this condition, if I extend u of x t, extend u of x t for x is positive, extend this to u of x t for every x belongs to R in this fashion. So, extend it to, so how do I do that? So, you call this extended function as u1 of x t, that is u of x t if it is positive. I extend it to as even function. If you do it as an even function, so u of minus x t, I know it is u for the positive side, that is how it is defined. X positive I know, so if you write u of minus x t, x should be negative. So, now this is how I extended, knowing u in the positive side, I defined u1 new function, that is for every x. If you do this, you can clearly see, if you want this to be continuous function, okay. So, you want this to be a solution. So, if this is a solution of the equation, it has to be twice differentiable and it is continuous. If you use the continuity, you can see that you differentiate ux of x t equal to minus ux of x t, is what is the differentiability at x equal to 0 it has to be continuous. That means ux at 0 t should be same as minus ux at 0 t. That means ux at 0 t has to be 0. So, if you extend as an even function and continuous at and continuous at x equal to 0 as this way, in this way if you define, you see that the boundary condition is automatically satisfied. Okay. And clearly u of x t is satisfying the wave equation, u of minus x t is also will also satisfy, because you are twice differentiating, minus 2 times minus sign will be plus. So, it does not matter. So, this also will satisfy the wave equation, and also initial conditions, so it will satisfy same initial conditions, okay, at x equal to 0, at t equal to 0 it will satisfy the same initial conditions, and then u satisfies u1 tt minus c square u1 xx equal to 0 for every x in R. Okay. Next, this satisfies the wave equation, then initial conditions are also satisfied. So, you can see that u1 at x0 is same as what happens to u1 at x0. So, you can easily see that this is u at x0, that is fx. Okay. Here also f of minus x, okay, when x is positive, x positive this, x negative is this. So, this you call it f1 of x. So, f1 is the function that is extending fx onto a negative side, that is as an even function. Okay. So, that you can see that fx, if you extend it as an even function, fx at 0 is actually 0 automatically, okay, df by dx at 0 is 0. So, f1 is a function that is extended function of fx onto the full real line. Similarly, you have other initial condition u1 t at x0, this will be, you can see this one. So, if you differentiate this with respect to t, this here ut at x0, that is gx, again that is when x is positive, and here also for negatives also this side, this when x is negative, here also you can differentiate with respect to t, that is ut minus x0. ut minus x0 is ut minus x. So, ut x0 is gx, ut minus x0 should be g of minus x. So, you have g of minus x here when x is negative. So, this is your g1 of x. So, u1 t, dou u1 by dou t at t equal to 0 is actually g1 function, that is an extended function of g onto the full real line. So, you have for u1 over a full real line that satisfies in the spatial domain, that satisfies the wave equation, and you have the initial data. These are your initial data, and the boundary condition is now automatically satisfied. Okay. And also along with that, because they are extended as an even functions f and g, and these are automatically satisfied, gx at 0 is also satisfied. So, when you are given a when you are given a problem for in the semi infinite domain, these f and g initial data should satisfy necessarily these conditions, then only in that under those conditions you are actually giving the solution. So, now it is direct evolution. So, this is now you have over a full real line, you have initial data. So, u1 of xt is simply D'Alembert solution, that is f1 of x plus ct plus g1 of x minus ct, sorry, f1 of f1 of x minus ct plus 1 by 2 c integral x naught to x, or should be x minus c t, x minus c t to x plus c t g1 of s ds. So, this is D'Alembert solution. So, what is my u of x t? This is defined for every x positive, for every x in real line, because it is u1. Now, you want only for x positive, that is u. U is, now you have to see, when x is again like earlier, when x is between 0 to c t, this is always positive f1. Here x minus c t is negative. So, if it is negative, f1 in the negative side, that is you have to take f of minus of x. So, in this case you have to write this as f1 of x plus c t plus f1 of c t minus x, okay, plus 1 by 2 c. Now, if you do this from 0 to x plus c t, g1 is positive. So, that is as it is. Now, when g1 is from x minus c t to 0, you split this integral to integral x minus c t to 0 and 0 to x plus c t. X minus c t to 0, g1 is negative. So, you have to write g1 of, so you can write this, you can separate it, split it, and you write x minus c t to 0, g1 of s is negative, s is negative in this interval. So, it should be g of minus s ds plus 0 to x plus c t, s is positive. So, it is same g of s ds, because g1 of s is g of s when s is positive. So, this is what you have for x is between 0 to c t. When x is greater than c t, so what happens? In this case, this is positive and this is also positive, okay. So, f1 is positive when the ordinate is positive, that means itself f1 is actually equal to f of itself. So, you can write directly f1 of x plus c t plus f1 of x minus c t, okay, plus 1 by 2 c x minus c t to x plus c t g of s ds, because s is always positive between x minus c t to x minus c t is positive, x plus c t is also positive. So, s is positive in this interval. So, g1 of s is g of s, this is what you have. So, if you actually rewrite, u of x t is, so this implies u of x t, the solution, final solution, you can write it as half f x plus c t plus f of c t minus x, and then this one plus 1 by 2 c. First integral, this integral you can evaluate as x minus c t to g of minus s ds. Just do the change of integration. So, you see that this is minus 0 to x minus c t g of minus s ds, and now we put g minus s as s1, let us say s1. So, minus ds will be ds1, and this is going to be 0 and minus x plus c t. So, that is c t minus x. So, this you have to replace for the first integral, 0 to c t minus x g of s ds, s1 is anyway dummy variable. So, we can replace with s, plus 0 to x plus c t g of s ds. This is for x between c t, 0 and c t. X greater than c t, there is nothing to change. So, you have half f of x plus c t plus f of x minus c t plus 1 by 2 c integral x minus c t to x plus c t g of s ds. This is for x greater than c t. Automatically f x at 0 is 0 satisfied, and g x is also satisfied, these two conditions are satisfied if you just equate u both sides, u limit equate this one like earlier u x t, as you make this limit u x t. Now here x goes to c t plus, here x goes to c t minus. By this you will get this one first condition, but if you do this any limits u t of x t, these limits, derivatives of this are also continuity of its derivative, that means c t plus as x goes to c t minus, this will give me this condition. So, we will see that automatically, but we do not have to do, because that is how we have seen that. Okay. The way we have extended as a even function, these are all automatically satisfied, that means you can easily now verify that u t is actually continuous. Okay. That means these are all actually satisfied, this is what that is how we extended, these are all these f x and g x at 0 are 0, this we already know, implies these you can see that these limits are continuous. Okay. Or in the opposite way, if you want this to be a solution, this has to be satisfied, that is already satisfied. Okay. That is how we extended the functions, f function we extended as a even function. So, if you are given a semi infinite wave equation on a semi infinite line, your initial data f and g should be satisfying these conditions, necessary conditions, that f derivative df by dx at 0 and dg by dx at 0 has to be 0. So, only for those for such problems only, for such initial data only we can give the solution like this. Okay. This is what we have seen. So, what we have shown so far is wave equation on a semi infinite line, on a semi infinite line. So, this is your x and this is your t. So, 0 to infinity is given. Okay. So, on the boundary you provided either u at 0 t is 0 or u x at 0 t equal to 0. So, this is what each of these cases we have seen how to find the solution from the D'Alembert solution, we derived the solution. Okay. The main problem is, you know that when you are solving the wave equation, you have the general solution, that is C1 of x plus Ct and C2 of x minus Ct. X plus Ct is always positive when x is positive and t is positive, but x minus Ct when x is positive, as t goes to, as t becomes bigger and bigger, x is fixed, x minus Ct can be negative. So, you want to fix that C2, C2 function should be defined on the negative axis. Okay. So, negative values you should know you should be able to find that function even on the negative side. So, that is another approach, actually we can do that. So, by directly applying the boundary condition, okay, by applying the boundary condition you can fix that C2. Okay. So, that approach is actually more general, as we see later on. So, we have these boundary value problems for the wave equation, either in the full domain or in the semi infinite domains, we have provided a solution. Okay. So, we still do not know whether this solution is unique or not. So, we can actually show in general there is a energy argument approach. Through this we can actually show that these initial boundary value problems solutions are unique. That means you take two solutions, to assume that you have two different solutions are possible, then you take the difference and show that by this energy argument it has to be, when you take the difference, that is whatever, that has to be 0, that means both the solutions have to be same. So, that means the solution is unique using that approach. Okay. So, we will see that how we can show by an energy argument, how we show that the solution is unique, okay, for these initial boundary value problems. So, to start with, to do that we take this wave equation. So, utt minus c square uxx is 0. Okay. So, you can take first now a domain, spatial domain as a full domain. This also works for any domain. Okay. So, this is what you have, the wave equation. So, what is the kinetic energy? You know that it models, it governs the governing equation. I mean when the spring is attached for an infinite string, you want to see the vibrations of a spring is governed by this equation. So, kinetic energy means u is the displacement, u of x t is the displacement, kinetic energy is half m v square, right, this is what we know. So, half, assume that you have a string which is whose density is constant rho. So, rho m is rho throughout and v is dou u by dou t, this square and then you integrate this all along the spatial domain, that is your kinetic energy throughout. Okay. So, you have a full minus infinity infinity, you have a string. So, you have a half m is there. Okay. This rho is rho into throughout this integration. So, you have rho is constant comes out, you have minus infinity infinity u t t square u t square is your kinetic condition kinetic energy. Okay. So, energy argument is you want to check whether this kinetic energy, whether this conserves, that means as a derivative of this, whether it is 0 or not, you want to see whether this is the only energy. Okay. This is the kinetic energy. We know that there is something called potential energy. Kinetic energy plus potential energy is constant, right, that is the total energy that should be conserved. So, if you take this time derivative, we will see what happens. So, because I do not know how to find this potential energy what we know from the Newton's law is mgh. So, h there is no, I do not know how to find this exactly what okay. So, we will see, we will define this potential energy that is equivalent to this. Okay. So, how do we do this? I find this derivative. So, I have 1 by 2 rho by 2 d dt of this minus infinity infinity u t square dt dx. Okay. So, you take this derivative inside, what you get is rho by 2 minus infinity infinity 2 u t dx. Okay. So, what is C? C we already know that C is square root of T by rho, we have seen this one. T is the magnitude of the tension of this string. Okay. So, where C is this. So, this is equal to, now I know from the equation you can substitute for utt. So, that is rho by 2 minus infinity infinity. So, rho by 2 goes, 2 goes. So, this 2 goes anyway. So, this is simply rho ut into uxx is c square. So, rho c square is actually c square is T by rho, that you can write T by rho into uxx dx, ut into uxx, this is what you found. This is equal to T times minus infinity infinity ut into uxx dx. So, I know that d dt of total energy is 0 because it is conserved, total energy is constant. So, and you take the derivative as for all times it should be same. So, the derivative should be 0. So, total energy is kinetic energy plus potential energy. So, this is 0 you want. So, you already know that d dt of Ke equal to something, okay, you got this is what we have. So, this if I can write this as something like d dt minus d dt of P if you can equate whatever you so whatever the right hand side here should be minus d dt of P like this, in this fashion if you write. So, whatever is in this derivative inside, okay, that is the potential energy you can define, which is equivalent to this mgh. So, we will see how to do that. So, this is now you can use the integration by parts here. If you do that t ux ut minus infinity minus integral minus infinity t is there. So, t ux and you have to differentiate this ut with respect to x. So, you have uxt, okay, dx, that is after. So, at infinity any you have a string of infinite distance. So, at infinity there should be 0, the displacement has to be 0 subside, right, or the slope should be 0, a velocity at infinity at extremes has to be 0. So, that this will be 0. So, what you have is this minus t minus infinity this one how to write as I want to take the derivative out. How do I write this derivative? You can simply say what you have is ux uxt dt. So, this I will write like this ddt of, you can say ddt of t integral minus infinity ux square d this is dx by the way, not dt, this is dx, okay. If you write like this, there is a half here. So, if you take this derivative inside, what you get is 2 ux, the 2 to goes ux uxt dx, this is what exactly what you have, okay. So, this is equivalent to this. Now, this implies d dt of ke plus, now you take this d dt of this something which I am defining as potential energy equal to 0. So, this is d dt of total energy is 0. So, implies I can define my potential energy. So, you can say potential energy. Potential energy of the spring is basically T by 2 minus infinity ux square dx, okay. So, you can get this potential energy like this, okay. So, once you see that, then you have a total energy is simply half integral minus infinity rho is there, rho by 2 ut square dx plus this potential energy is T by 2 minus infinity ux square dx, okay. So, this is what is the total energy, you can say total energy. So, you see that total energy is 0. So, that is how you find, okay. If your string of infinite length minus infinity is satisfying the wave equation, and then your total energy of that string is this one, which is conserved, whose time derivative is 0, okay. This is what we find. Now, what we do is now you take this the problem. So, your problem is utt minus c square uxx equal to 0, x belongs to R, and u at x0 is fx initial data. This is you have two initial data, that is fx gx. This is the problem. So, you have a initial value problem for the full real line. So, you have given this for this problem, you have given D'Alembert solution. Now, you assume, so you do not know whether that is the only solution. Okay. So, you have one solution, now you have a solution, that is D'Alembert solution, you want to know whether this is the only solution you have for this problem. Okay. So, initial value problem, because there is no boundary here, boundary is full, this is t. Okay. So, t is this, you have x axis is, and this is your t axis. Okay. And this is the only boundary, that is where you have initial data. Okay, at t equal to 0 you have provided. So, you have for this you want to check whether uniqueness, whether you have a unique solution or not. Let u1 of xt and u2 of xt be two solutions. So, if you take them as two solutions, then they satisfy this one. Okay. So, you can see that u1 tt, so u1 u2 satisfy wave equation. Okay. And what happens to the initial data? u1 satisfies that, right, and w, let us call this w, that is u1 minus u2 also satisfies the wave equation. Okay. This satisfies wave equation, the difference also satisfies wave equation clearly, because it is a linear equation. And because u1 and u2 satisfying this initial data, w also satisfies. So, w at x0 equal to 0, w is u1 at x0 minus u2 at x0, u1 at x0 is fx, u2 at x0 is also fx, because u1 and u2 are two solutions of this initial value problem, the problem star. And w at x0 is 0, wt at x0 is also 0 because of this. u1t x0 is gx, u2t x0 is also gx. So, the difference, okay, wt is u1t minus u2t at x0, each is gx minus gx, that is 0. So, this is what you satisfy, w actually satisfying the wave equation with this 0 initial data. Okay. Now, I consider my energy function. Okay. E of, let us define this EW of t. I define for all times what is my energy. So, from this is my energy. So, instead of you write this energy is rho by 2, kinetic energy is minus infinity to infinity, wt at xt square, okay, this square dx plus t by 2e minus infinity to infinity wx of xt whole square dx. This is what is the total energy. This is how I define, actually we have, right, this is how we have seen. Now, if you put w at x0 t equal to 0, E of w of 0, okay, what if at t equal to 0, wt at x0 is 0, wt at x0 is also 0. So, this implies w at x0 is 0 means wx at x0 is also 0. Okay. So, that means this is also 0, this is 0, this is from the second condition, second initial data. So, this is actually 0. Okay. The way if you define this as energy, and this is your energy function, initially the total energy is 0. Okay. That implies E of, because its energy is conserved, EW of t has to be 0 for every t. That means, and you can see what is that EW of t is 0 means this is 0, this whole thing is 0, that means this is only positive integral square function, rho is positive, t is positive. So, that means w t at x t and w x at x t. So, those partial derivatives have to be 0 for every t, okay, for every t and for every x has to be 0, then only positive something, see integrand is positive. If this is integral with the positive integrand is 0 means integrand has to be 0, okay. So, that is the idea. So, this is 0, each part has to be 0. So, this is 0 separately and this is 0 separately, which I am writing as this, okay, and this is actually gradient of w, okay. If this is 0 for every x and t, w has to be constant, okay, that is w at 0, and which we already know that it is 0, okay. W has to be constant, w, so w is basically w of t, okay, w of x and t, right. So, you can say simply w of x and x comma t has to be constant, okay. That means w at x 0, right. Let me write this is constant, w at x t is constant, but we know that w at x 0 is 0. Why? This is the initial condition, w at x 0 is 0, implies w at x t has to be 0 for every x and t. So, what is w? u1 of x t minus u2 of x t is equal to 0. That implies u1 of x t should be same as u2 of x t for every x and t. So, what does it mean? This is whatever, if you assume these are, if you assume two solutions of this initial value problem, they have to be same, okay. This is, how did I do that? This is through this energy argument. So, you know that potential energy is half mv square. So, that we have seen half mv square is, I can easily write, that is why I made it, okay. I could nicely write in terms of this displacement, string displacement or spring velocity, okay. A string velocity you can write its kinetic energy. I cannot write this potential energy. So, but instead indirectly I know that energy is conserved. So, I can if I can put it in this form, I can identify what is my potential energy. So, that is how I identified my potential energy. So, implies total energy is here. So, through this total energy function, if you assume two solutions, two different solutions, if you consider, then they satisfy this problem with this initial data, okay, with this initial data, and then you define the energy of this w function, okay, as this. Instead of you write in terms of, for this problem what is the energy in terms of wt wx square. So, if you do this, you know that because of the initial data energy is 0 at initially, implies energy is conserved, implies for all times this is 0. That implies if you write this EW of t is 0, that means wt wx has to be 0, that is gradient of w is 0, that means w is constant. But from the initial data w at x 0 is 0, that implies w of x t has to be 0 for all times, okay. So, if this is constant, that constant has to be 0. So, that is how I found is 0. So, implies you have found that the solution is unique for the initial value problem. The same proof works even if you take the problem of if you replace this initial value problem with the problem on the semi infinite domain with the boundary data at x equal to 0, okay, or any x domain with the initial data and the boundary data, you can apply this energy argument and show that a solution is unique, okay. Let us not do that, let us not repeat this, but you can replace this initial value problem with any other problem. So, that means you have to take the wave equation, you change this x domain. If you change this to 0 to infinity, you have to provide the boundary condition. So, that all together you form the same argument, you can show that then the uniqueness proof same u1 and u2 satisfying that problem, and you define this energy argument energy, and you show that finally W is actually 0 identically for all x and t. That shows that u1 and u2 you do not have two different solutions. So, that implies D element solution is the solution of the initial value problem of the wave equation over the full real line. And similarly, you can even for semi infinite string equation, that is wave equation on 0 to infinity with boundary data, whatever you have given so far two boundary data, that is u is a fixed string is fixed with a 0 displacement at x equal to 0, or its slope is 0, that means it is free. The edge is edge of one edge of the, that means the at 0 you have this string is free, left free, for which these two problems also solution is unique. By the same argument you can show that solution is unique, that implies you have given a solution that should be the only the solution, okay, provided f and g satisfying the conditions, okay. If based on the boundary data, if ux0 u0 t equal to 0, if that is your boundary data, you extend it as an odd function. So, f and g has to satisfy f of 0 is 0, f of g of 0 equal to 0. So, for those initial data you have the solution, okay. Similarly, for the other boundary data, that is ux at 0 t equal to 0, if you are given that as the boundary data for the semi infinite string, then for all f and g initial data with dou f by dou x at x equal to 0 and dou g by dou x at x equal to 0 has to be 0, they are the necessary conditions. For those f and g initial data you have the solution for the wave equation with initial data and the boundary data, okay. So far you have given only two types of boundary for the semi infinite string, okay, that is at x equal to 0 you have provided u is 0 and ux equal to 0 at this point. You have initial data at t equal to 0, but at the boundary you have only here, and these are the two, either this or this is given, and you can actually make a combination of this with some constant equal to 0, okay, ux into some k, or you if or you can also give a different ways, okay. You can actually provide u at 0 t is actually some, it is non-zero condition, you can give some function of t, or u x plus k is some constant times u is also 0 at x equal to 0 for every t, that is also you can give. This is if you can attach this point at x equal to 0 with a spring of stiffness k, you can attach, so that this slope is actually proportional to the displacement with this constant, okay. That is what if you do with a spring of stiffness k, if you attach at x equal to 0, this is the condition for the spring, okay. This one you can attach in such a way that this is u is the displacement all the time changing, okay. This may be pt may be all the time varying, so it may be some oscillatory function p of t, okay. So we have seen if you are given these two boundary conditions, you have seen nicely you can extend it as a odd or even functions and get the solution from the D element solution. What happens if you do this way? If you are given these boundary data, that may not work. So the more general approach is just directly working from the general solution of the wave equation, okay. That we will see in the next video, okay, with some remarks. So I will try to redo these semi infinite wave equation problems, okay, whatever we have done so far for these boundary value problems, we do that approach, and so that these the other two boundary conditions, general boundary conditions, are similarly can be worked out, okay. I will try to redo whatever I have done for the semi infinite boundary value problems, okay, initial boundary value problems for the wave equation on the semi infinite line 0 to infinity, I will try to redo in a more general approach. Okay. So, that I will see in the next video, and then we will move on to a finite string, that is where we make use of our Sturm-Liouville theory. Okay. So, these are the things we will see in the next few videos. Thank you very much.